Hi everyone. In this video I'm just gonna kind of wrap up this concept of calculation of heat with another example. So just a reminder that heat is the equation for heat. It can be expressed in three different ways. You can calculate it as heat capacity times delta T, the mass times specific heat times delta T, or the molar heat capacity times the number of moles times delta T. In the example we did in the previous video, we talked about this idea of heat capacity times delta T, right, in example 1 that we did in the previous video, this example right here. Now we're going to do another example with specific heat capacity. And again, the idea here is this same concept that I mentioned in the very beginning, which is that if you have two systems, like for example in this case, let's say you have a piece of metal that's at a higher temperature and you put that into a beaker containing water at a lower temperature, the metal at the higher temperature will release energy in the form of heat and the water will absorb that energy. Because the two systems are next to each other, then there's no other transfer to the air, we assume. Then the amount of heat transferred by the metal has to be equal to the amount of heat absorbed by the water. Okay, in other words, Q metal has to be equal to Q of water, and in this case one of them releases, the other one absorbs. So the way you think about it is that one of them is if it's releasing, you can say it's negative Q, and then if it's absorbing, it's just positive Q. Okay, so really this equation should be negative Q metal equals Q of water. And then of course Q itself is expressed as this equation, mc delta T if you have specific heat, and then this of course is mc delta T as well, but then for water. Okay, so let's look at this example real quick here to illustrate this concept. So you have basically the situation that we just talked about. You have some sample of metal that's heated to this temperature. You then take that metal and then put it into a beaker containing water. The temperature of the water rose from 25 to 30 degrees Celsius. You're asked to find what the metal is from that specific heat table. Okay, so based on that question, it should be fairly clear that what you have to do is calculate the specific heat of the metal, right? Because then if you find that number, you can then go to this table and then compare the number you calculate to one of these metals, and hopefully it will match one of them. Okay, so here I rewrote all the information from the question. You have the information that we're given initial temperature of the metal at 61.67. We put that metal into the water, and then the water initially temperature is at 25. Once we equilibrate the temperature, actually I made a mistake here, this should be 30. The final temperature after we mix these two things together and it equilibrates, it's at 30 degrees Celsius, and they're both the same, right? So that's what we refer to as thermal equilibrium. And then the mass of the metal initially is this, the mass of water is this, and of course the specific heat of water is assumed to be given in this case, which is 4.18 joules per gram degree Celsius. Okay, and then what we're asked to do is really calculate the specific heat of the metal and then match that to one of the metals listed in that table. If you think about it again, the equation should be like this. One of the systems releases energy, that's the metal. So you can think of it as the negative Q of the metal is equal to the Q of the water. Okay? The water is the one absorbing energy. So we can first calculate Q of water and then later on relate it to the Q of the metal. So if you think about it, Q of water, of course, is just M mass of water times delta times C of water times delta T of water. Okay, so if I were to plug in all those numbers, then what I get is 26.7, right, grams is the mass of water, and then C sub S is 4.18 joules per gram degree Celsius, and then I have 5 degrees Celsius is my temperature difference, because it's just 30, which is final, minus initial, which is 25. Okay, and if I make this calculation, the number I get here as the heat that's released, or that's absorbed, I'm sorry, is 558.564 joules. Okay, 564 joules. Now this is the same amount of heat that's released by the metal. So you can say that heat released by metal is equal to negative 558.564 joules, right? Because remember that the metal releases, so it has to be in a negative quantity. That's basically just like writing negative Q metal is equal to 558, therefore Q metal is negative 558, okay? The negative is important because it indicates that one system is releasing energy. Okay, and then what you do from this point on is you just solve this problem by saying that this is equal to M of metal times the C of metal times C sub S of metal times its delta T. Now we know the M of metal, we know the delta T, so we can just solve for C sub S of metal. C sub S of metal is going to be Q, which is negative 558, 564 joules, right? 564 joules, and then that divided by the mass of the metal, which is 19.6 grams. And then now comes the part that's a little tricky, but actually if you think about it, it should make sense. The final temperature of the metal, remember, is 30. The initial temperature is 61.67. So as a result, when you do this calculation, okay, so this is 61.67 degrees Celsius. If you make this calculation, you see that you're going to get a negative number here, but that negative number will cancel with the negative sign at the top, so then overall you get a positive number, because you remember that heat capacity, the specific heat has to be a positive number, okay? And if you make that calculation, what you get is around 0.9 joules per grams degree Celsius. And if you look up the table from the table I showed you in the PowerPoint earlier, you go back to the PowerPoint real quick and show you that table, you see that it's this matches with aluminum, okay? So 0.9. So then the metal in this case is aluminum is our answer, okay? All right. So what I want to do here is just kind of wrap up this section on heat calculation by reminding you again why we're doing this. The reason we're doing this, again, remember, is that we want in the end to be able to measure and calculate delta E for a particular reaction, okay? And in order to do that, we have to be able to calculate Q and W, because delta E is equal to Q and W, because those are the two methods of energy transfer that we know of, okay? In the previous section, in 6b, we talked about calculating W. Now in this section, in 6c, we talk about calculating Q. And now we have equations for both of them. Remember, the W equation is the negative P external times delta V. That's the expansion work. The Q is MC delta T, the one that we just learned. Combining these two allows us then to add them up and calculate our delta E, which is the quantity of interest to us. Okay?